Hey everybody. We have very few people show up today.
Maybe some will join late.
I thought being late was only happened in physical classes, but
Yeah.
I am amazed with the regularity it happens in online classes also. Uh, I don't know, but I myself have started coming late, becoming late. I mean, not deliberately, but it just happens that I'm late. I don't know. Anyway, so we were going to discuss two papers today, and did anybody happen to look at them? The two papers. One is by Daniel Hartle and Roy Kishne's group, the 2007 paper in Science, and the other one was from LT Lenski's group in 2011. Uh, did anybody take a look? I mean, I know I didn't ask you to, but I did ask you to come having thought about that graph. Does anybody know what I'm talking about?
Yeah.
Okay. Others? Shreya?
Yes, sir, I know what you're talking about, but I haven't read the papers.
Cool. Namrata, yes, tell me.
Yes, sir. In the first paper, that is about second order selection.
Correct.
They're talking about eventual losers are winners because, like, initially for first few generations, we
Yeah.
might think that the ones which are having best mutation at that particular instance will be the winners further.
Right.
But during the course of evolution, few more mutations can happen due to some epistasis and all.
Correct.
Other strains will become the eventual winners.
Absolutely. Absolutely. Correct. Anirudh?
And in,
Uh,
and
so,
in the second paper,
mhm.
in the asexual population, there might be different mutation rates and uh, what, different kinds of beneficial mutations arriving, and few might go for fixation and few might not. So they're developing a model to pick one most probable mutation rate and beneficial that selection coefficient, so that they can go for the entire model only using those
Yeah.
values, like
Yeah.
effective ones.
Yeah. The second paper is a tricky one, and that's what I want to spend most of the time today talking about. I mean, also, I mean, based on your very brief descriptions about the two papers, it's apparent that the first paper you've clearly understood very well. But the second paper is a lot more trickier. That's why I'll spend most of the time today discussing the second one. Anirudh, go ahead.
I hadn't gone through the two papers, but
Had not.
no, I have
Okay.
not.
Okay.
I was going through the Gould's paper though on which was part of the assignment, and I
Yeah.
had
Yeah.
a question regarding
Right.
that. So can I ask you that right now?
You can, but I would like to go through Good's write-up that everybody has sent me before I discuss that. So I was hoping to do it on
No,
Friday.
it's not regarding Gould's paper per se. It's
Okay.
just a general question.
Go ahead.
So um, because Gould was talking about body plan and all of
Mhm.
the architecture and everything, it got me thinking about the neck of a giraffe, for example.
Mhm.
So we assume that the the height, the length of a giraffe's neck is based on the adaptation that it had to reach certain heights because the lower ones were in competition.
Yeah.
But what's weird to me is that uh, mutation can, so if the giraffe is at a certain height, let's say the neck of the giraffe is at a certain height x, um, the any mutation can only make it dx plus dx, where
Okay.
dx is very less compared to the actual height
Right.
at that moment. So uh, and if the height of a tree, let's say, is x plus is x plus 3 dx,
Then it's
then
no advantage.
there is no advantage. So I'm really confused as to how evolution could have taken, because apparently, like the way evolution should work, there should be a continuous array of slight adaptations that
Yeah.
it's like a continuous distribution of heights of trees.
Right.
So how is it seemed like Gould's argument was better in that. So why I think Gould's argument here is because he stated that maybe uh, this is a secondary adaptation. Also, although it doesn't look like a secondary adaptation, it seems so obvious that the height is the reason. Of the reason for the height is most probably competition at lower levels. Could it be that developmental changes could have affected? There could, I mean, because of pleiotropy, the height was not the only reason
Yeah.
that was selected for, though it seems very unlikely. But the
Yeah.
other one also seems unlikely. That's why I was
Yeah.
confused.
Yeah. No, I agree. I don't really have a good answer. I don't really know. I not without looking up references. I can't answer that right now.
Okay.
Yeah.
Okay.
Yeah. All right. I guess it's just us today. So let's start. So do you guys remember the graph that I asked you to sketch in your mind or paper and for today's class? Does anybody remember that?
Yeah. So it was on the x-axis we need selection coefficients
Yeah.
and greater than 1, greater than 0, and on the y-axis probability of these occurring.
Correct.
So as we discussed in some previous classes, it should look like an exponentially decreasing curve.
Correct.
But the paper, I think it includes clonal interference and suggests that there can be many variations in this.
Right. Again, I think that's a tricky paper. Hence, that's not the issue. Clonal interference is not the issue, and I'll come back to that in a second. Others? Do we know what Yash is talking about or not know? That forms a starting point of where we're going to start from today, for today.
So even I thought of similar kind of distributions.
Okay. Cool. Okay. Shreya?
Yeah, even I agree with the exponentially decreasing graph.
Okay. All right. Anirudh, Sakshi, do we know what is being talked about?
So can we just discuss this again?
All right. Anirudh? Maybe he fell asleep. All right. So this is referred to as something called a distribution of fitness effects. And I'll just do this very briefly. The idea is as follows, and it's a conceptual idea. We'll worry about the determination of this distribution in a little bit. But conceptually, it's this, that you have a genotype G and the organism, and we're thinking bacteria, we're not talking sexual reproduction. Organism with genotype G has a fitness F0. And what we'll do is if we introduce 1 point mutation randomly, okay, only 1 point mutation. So in this case, it happens at this particular location. And if that point mutation is deleterious or neutral, which means if it either decreases fitness or doesn't change fitness at all, and obviously this is environment context, because remember, fitness is a function of genotype and the environment. So if this 1 point mutation either decreases or doesn't bring any change in the fitness, then we don't care about it. We discard that mutation. We are only interested on those point mutations which increase fitness. So we are only interested in beneficial mutations, which automatically implies we are interested in mutations with selection coefficient greater than 0. So, guys, just 1 second. So, actually, can I take this phone call? It's kind of important. I'll just take 2 minutes. Sorry about that. All right. So, so we are only interested in beneficial mutations here. So this is a beneficial mutation, and we note the corresponding selection coefficient associated with it, which is just going to be F1 minus F0 by F1, whereas F1 is the fitness of this beneficial mutation. Then we go back, so we note this S1, right? Then we go back to the original genotype, introduce another point mutation in the same genotype, which is beneficial in nature, and note the corresponding S2. Remember, these beneficial mutations are being introduced completely randomly, right? Again, conceptually, we will worry about the experimental determination of it. So we keep doing this over and over again, and let's say we do this thousands of times, okay? So what we have is, in this genotype, when we introduce a beneficial mutation, what are the corresponding S's for that beneficial mutation in this parent genotype? So at the end of this collecting information about these thousands of selection coefficients, what we are going to do is make this graph. So we are going to draw bins here, and let's say we are going to ask that how many of these thousands of beneficial mutations had a selection coefficient which was between 0 and 0.01. So of this thousands of ones tested, maybe I'm making stuff up here, but maybe this 15% had a selection coefficient between 0 and 0.01. Then we ask how many had a selection coefficient between 0.01 and 0.02. So this is those beneficial mutations which are imparting a benefit between 1% and 2%. So this is 20%, then this is 18%, and blah, blah, blah. You keep going till every beneficial mutation is accounted for. And at the end of it, you get some sort of a distribution associated with beneficial mutations. And we've had this discussion previously in one of the classes where we asked that what sort of distribution of beneficial mutation agrees with our intuition of how beneficial mutations would be distributed. And the consensus we reached there was it should be some sort of a decreasing function. Essentially what we are saying is that beneficial mutations of small magnitude are much more likely, and it's increasingly rare to find a beneficial mutation of a large magnitude. So the distribution will be some sort of a decreasing function, and there is a lot of theory work that's been done on this. And the consensus from theory is that it should be an exponentially distributed exponential distribution, which defines this distribution of effects of beneficial mutations. This distribution is called distribution of fitness effects, or DFE. Right? So DFE is a term that if you're studying evolution, you'll come across quite frequently, because it's obviously important, because DFE is sort of DFE of an organism in a particular environment is telling you the availability of the beneficial mutations in its evolutionary trajectory, and depending on what is the distribution, the sampling of beneficial mutations is going to happen from that distribution, and thus is going to decide the evolutionary fate of this population. So we are not going to be talking of DFE of deleterious mutations, which will be on the other side of this for negative S's, right? But let me just add one comment that finding DFEs of deleterious mutations is a much more harder task, both in experiments and in theory, and there is much less known about DFE of deleterious mutations. You could also argue that we are less interested in DFE of deleterious mutations because these are the variations that are going to get weeded out from the population anyway. So our interest is much more on the positive side of this graph rather than this side. But there is definitely work done to determine DFE of deleterious mutations, but we won't get into that. So now, what is our expectation? And the expectation is something that we have discussed before, that some sort of a decreasing function. The question that this paper starts with is that how do we determine this distribution experimentally? Okay. That is the central question that this paper is dealing with. Determination of a DFE for a bacterium, E. coli in this case, experimentally. Okay, again, a lot of theory work, but this paper is a really cool attempt at finding the DFE experimentally, right? And at least I find it really interesting because at the end of it, they actually say that you can't find DFE, and you can't find DFE using this particular approach. Okay, and so in that sense, it's a failed attempt at finding DFE for reasons that we'll discuss today. But I think the reasons for that are extremely interesting. So that's the bigger context in which this paper is written. The two lead authors, Daniel Hartle and Roy Keshney, are sort of the leading people in this area. Questions, comments up until now? Okay. So what is the approach that they use? Right? How do they find the DFE? The approach that they use is that they use fluorescent proteins. They make two populations of E. coli, right? And the genetic constructs can be thought of as follows. They create two variants of E. coli. So in one variant, there is a promoter. So this is the rest of the genome. There is a promoter which is driving expression of what is called a yellow fluorescent protein, or YFP. This promoter is such that in the environment in which they are going to test the DFE, this promoter is always active. So it's continuously driving transcription. Hence, in this particular environment, YFP is being continuously made, and every cell which carries this particular construct is going to glow and look yellow under a microscope or in a fax or any other such analytical device. Right? So this construct, everybody carrying this construct is going to look yellow. The second construct is exactly identical to the first one, except for the fact that instead of yellow, it's driving a fluorescent protein which is cyan in color. So this is bluish green fluorescence. The promoter is the same. The environment in which it's going to be grown is exactly the same. And the only difference is that this is driving yellow, this is driving cyan. Does that make sense so far?
Yes.
All right, cool. Now what they're going to do. Okay, so I had a picture of this. So this is what these fluorescent proteins look like. So this is a plate of solid media, and on this plate they have streaked four different versions of E. coli which are carrying these different fluorescent proteins. So this is what YFP looks like. I mean, the wavelength is more in the yellow spectrum, but it looks sort of green here. This is blue. This is cyan, bottom right, and this is just a variant of GFP, right? So for our experiment, we are interested in the two versions that we are interested in are the top left and the bottom right. And the choice of these two is very deliberate, because the way you detect these fluorescent bacteria is that each fluorescent protein has a particular excitation wavelength. So you shine light of a particular wavelength, and these proteins absorb that light and they emit light at a particular wavelength. And depending on what is the wavelength that the light is being emitted, they appear blue or green or yellow or red. And there are many more versions now, right? So each of these proteins has an excitation spectra and an emission spectra. And working with cyan and blue has this advantage that their excitation and emissions spectra are sort of far apart from each other, such that one's excitation doesn't really interfere with the other's emission and vice versa. So they're sort of completely delinked with each other. Suppose you were using green and yellow fluorescent proteins, that's not a good choice, because green and yellow, you know, in the spectrum WIBGYOR are right next to each other, and their excitation and emission will overlap with each other, and it will be really hard to decouple and understand which of the emission is coming from green and which of the emission is coming from yellow. So in that sense, cyan and green is a good choice. Green and red would be a good choice. So you have to be careful when you're working with multiple fluorescent proteins that their excitation and emission spectra do not convolute the observations. All right. So next, what they did is, I think, a really cool. Again, I am a big fan of this paper. So they do the following: that at t equal to 0, they take a chemostat, right? And what they do to start things off, they put equal number of the YFP carrying individuals, which are open circles, and an equal number of CFP carrying individuals, which are these closed circles. So they put equal number of bacteria in these in this chemostat, and they start the chemostat's operation with that particular setting. Hence, at t equal to 0, the number of YFP carrying bacteria by number of CFP carrying bacteria, the ratio is just 1, which implies that at any given point in time, I can sample what is present in the chemostat and get a ratio of the yellow fluorescence and the cyan fluorescence coming out of this chemostat. So because the number is equal, the ratio also will be equal here. Any questions up until this point? Questions, comments, doubts, anything? Okay. All right. Now what I'm going to do is let this chemostat run forward in time, right? Let them divide, and some of them are going to get washed away, and obviously new divisions are happening because there is fresh media being fed into it. And what I'm going to be monitoring is the yellow to cyan ratio with time, right? It's 1, and remember that the open and the closed bacteria, well, green, yellow and cyan bacteria have identical fitness. The rest of the genome is absolutely identical, and the only difference is that in one, the promoter is driving yellow, and in the other, the promoter is driving cyan. And hence, and both these are close enough such that the burden associated with producing cyan is equal to the burden associated with producing yellow. So the additional load of producing the only thing that's different in the genome is which fluorescent protein is being expressed, and the cost associated with either one is more or less the same. So it doesn't matter. It's not as if that the yellow producing bacteria are less fit than the cyan producing bacteria. The cost associated with that production is the same. Most of these proteins are not very large. So I'm going to monitor the ratio of yellow to cyan with time, and obviously it starts with 1. Now tell me, what do you expect will happen? Is the question clear?
So could you just repeat the last part of the question? I got disconnected because of network issues.
Yeah. So the question is that you start with an equal number of yellow and cyan carrying bacteria. So the ratio of fluorescence, yellow fluorescence and the cyan fluorescence is 1:1 at t equal to 0. And I'm going to let growth happen in the chemostat. And periodically, I'm just going to keep watching what happens to the ratio of yellow is to cyan. And obviously it starts with 1, and since fitness of both genotypes is identical, it stays at 1. And the numbers that I have added at t equal to 0 is large enough such that this is largely independent of drift. I mean, if I had started with 4 each, there is a chance that 2 out of the 4 open ones get washed away, and then drift decides the fate of the population. But that's not the case here. The number that I've started with is large enough such that drift is largely irrelevant here. In such a scenario, what will happen next? Anybody?
So we can expect that one of them will grow in number.
Both will grow in number, right? Why one of them?
I mean, yeah, both will grow in number, but so in that case, it should remain 1 at all times.
Correct. Correct. That's our starting point. Yes.
Okay.
But do you think something will happen along the way?
Mutations can change how each of the 2 variants is growing, right?
Mm-hmm.
So one can grow faster.
Mm-hmm.
So we will see a dip or rise in the ratio.
Exactly. Yep. Anirudh, you were saying something?
No, so I was just asking, how many samples do you measure at each time point, or is it just one sample that you collect and measure the fitness? I haven't read the paper, so
Yeah. I'm not sure I understand the question. What do you mean? Yeah.
So you measure the. Can you go back to the graph if you don't mind?
Yeah. Right.
So you're measuring yellow by cyan.
Correct.
The sample's yellow by cyan ratio.
Yes.
So how many samples do you take per time? Is this an average, or is it just one sample's value?
Yeah. I mean, if go ahead, complete your question.
No, that's my question. I mean, is it just one sample, or do you collect the average value?
Yeah. So I don't know. Have you worked with fluorescent proteins before?
Just for normal after fixing cells and then looking at nucleus and all of them.
Oh, okay. Okay.
Yeah, that kind.
Yeah. So these are eukaryotic cells then. Yeah. So see, the way it would work is your chemostat in an experimental setup would be of the order of few hundred milliliters. Okay, I don't remember the exact size that you use, but it'd be like maybe 200 milliliters chemostat or 500 milliliters max. Okay, and when you are sampling, you would take a mil max. Okay, not more than that. And when you are measuring fluorescence, you would typically do this either in a flow cytometer, or you would do this in a microplate reader. And for either one of those, you are not going to use maximum 100 microliters. Okay. So in terms of the volume that you are using to measure a sample's fluorescence, it's very, very small. But the number of cells that you will be measuring the fluorescence for will be in, again, if it's a microplate reader, it will be upwards of 1 million cells. If it's a flow cytometer, it will again be at least 100,000 cells of each kind. So that is what is going to give you one reading. And now if at one time point, if I were to take 3 different readings, the deviation that I would get using these techniques is actually going to be next to nothing. Okay? With that large a sample size, it will be just the same. Does that answer your question?
Yeah.
Right. And when you, for an experiment like this, you can't have 3 different chemostats and take their reading and average it out. Can you tell me why?
Because the mutations would be very different here.
Absolutely. The timing of the mutation, the effect of the mutation is going to be different. So that doesn't make any sense, right? It has to be from the same. It has to be from the same reactor. But the measurements involved here are going to be so robust, and you will process so many cells at any particular point that taking 3 samples at a particular point or 1 sample, it's going to be the same. Yeah. In a eukaryotic cell, it's more problematic because then you have sample size effects, and especially if you're doing microscopy, because microscopy is going to limit you to the number of cells that you're going to be processing. But this
we
is
kind of take patches within a
right.
slide.
So you will take a certain field view, right? And that field view might have 50 cells, 100 cells,
right,
but not too much more than that. But but the techniques that will be used in this particular experiment will process millions of cells.
Okay.
So the sampling effects are going to be much larger in the type of experiment that you are thinking of, but not here. Right? All right. So tell me, what do we expect?
So in this case, do we wait for mutations to arise?
You tell me, in this experiment, what should we do? Remember, our goal is to measure DFE. What should we do? Let's think of one run of this experiment. What's going to be, and the readout that I'm measuring from my experiment is the ratio of yellow to cyan. That's the readout that I'm measuring. So we'll worry about how to get DFE from that later. But how is the readout going to change over time? So I've obviously purposefully only kept it at 1. But then what's going to happen? Can we anticipate that?
No, I think it's just one realization, right? So it could move either up or below based on which cell receives the mutation first.
Cool, fine, agreed. But
it could move up again because another the let's say the yellow one now has a better mutation later on, then it could again move up, I guess.
No, if yellow has a mutation, it will move down. Because remember, this is the number of yellow individuals.
Oh, okay. Yeah, my bad.
So if yellow picks a beneficial mutation, the curve moves down. Right. Because you have more yellow now, right?
I'm just saying that it could move down, but it could also move up if yellow hasn't been fixed completely.
Agreed. Yeah. So the trajectory could be any. So let's say if the first beneficial mutation was in cyan, then this would move up. right? But before that mutation reached fixation, one of the yellow individuals could pick up a bigger beneficial mutation, and hence that curve starts to move down. Does that agree with everybody?
Yes, sir.
Yes, sir.
So what are we interested in? What would you like to extract from this experiment? Remember, we are interested in DFE of the original genotype. Any ideas, thoughts?
I'm not sure if it'll work this way, but I think probably we'll get the relative fitness between both of the types, and then we'll have to normalize one of them to get X is to 1 type ratio, probably to get 1 plus S, probably. I'm not very sure though.
No, absolutely right. Absolutely. So this is what's going to happen. That something's going to happen. I mean, not something, we know what's going to happen. One of the individuals in these populations is going to pick up a beneficial mutation. And in this case, it's a cyan individual which picks up a beneficial mutation. So I mean, this could be confusing, I guess. The ratio yellow is to cyan. Oh, this could be number of yellow and number of cyan. Think of it like this. So the number of cyan guys is increasing here. So it's the cyan which has picked up a beneficial mutation, and then a yellow individual picks up a beneficial mutation which is larger than the first beneficial mutation, and it goes in the opposite direction. And this will keep on happening, right? But we are not interested in any of this. That's because we are only interested in the first beneficial mutation and its selection coefficient associated with it. And that's because of the reason that I am only interested in DFE of this genotype. Once another genotype occurs the equation, I'm not interested in that, right? So the only part of this graph that I'm interested in is what happens when the first beneficial mutation occurs in this population. So what I'm going to do is, so obviously, so this is a beneficial mutation. Now what I'm interested in is that I from this data, I can calculate the rate at which the cyan population is sort of eating into the yellow population. I can calculate that rate. If I do that, then from this rate, I can back calculate that what would have been the selection coefficient associated with this beneficial mutation. And remember that beneficial mutation happened in one individual here. And that genotype is actually outcompeting not only, which one was up, yellow? Yeah. So when this beneficial mutation occurs in this one cyan individual, that cyan individual is outcompeting all these yellow and also all these cyan. So actually we have, at this particular point in time, we have 3 genotypes in the population: the original yellow, the original cyan, and this new cyan. And what is happening is that it's a new cyan which is eating into both the original yellow and the original cyan genotype. So, but anyway, that's a detail. What we can do is the rate at which yellow is being forced out of the chemostat is going to be proportional to the selection coefficient associated with the beneficial mutation that happened here. So we can do those calculations, and they're a little bit involved, so we'll skip that. But we get the S of the beneficial mutation, right? Now what should I do if I want the DFE, right? My goal was to, from this experiment, get a DFE of the original genotype. What I have through this experiment is one S. We have S associated with one beneficial mutation. What should I do next?
Then we start again.
Start again, absolutely.
Repeat.
What was that?
We take replicate
Yeah.
readings.
We do this experiment again, right? And of course, when we do this again, another beneficial mutation is going to happen now, and it's going to eat into the other thing depending on the selection coefficient associated with this beneficial mutation that happens in the second run of this experiment, right? And there are two variables here. One is the time it takes for this beneficial mutation, and the rate at which it's eating. So we get two pieces of information from each particular run, and the time it takes sort of gives me an idea of what is the mutation rate associated with this population, right? Of course, this time is going to be a distribution, but when I repeat this experiment many times, I'm going to get a distribution of the time at which this first mutation occurs. And hence, that gives me an idea of the mutation rate associated with this population, right? And remember, this is the mutation rate of beneficial mutations only, because I couldn't care about neutral and deleterious mutations here. Those mutations are happening, but this time tells me what is the mutation rate associated with the beneficial mutations in this particular genotype. So this is what they did, and this is sort of one figure from that paper. This is what you end up getting, and you see that slopes change. Like this dark line, it flattens out here. This dark line is going up, but then it starts coming down, and all sorts of trajectories play out. But not interested in any of that. What they are interested in is the slope the first time the line changes from. So they've taken a log here, so the 1 becomes a 0 here. What they are interested in is the first time the slope changes from 0, right? That's the information we're interested in. And the other piece that they extract from here is at what time does this slope become non-zero, right? So these two pieces of information is what they arise from, what they take home from this particular figure. The later dynamics is not relevant for the question that they are asking, right? This line, for instance, it starts to go down with a very gentle slope, but then it picks up the other color picks up a mutation presumably, and it goes up very rapidly. So this is not relevant anyway. So they do it of the order of 100 times. What then? Remember, my goal is to find the DFE, right? And I've done this experiment 100 times. So what I have at the end of 100 times is 100 values of S. What do I do next? Yes, sorry, I cut you off.
So we have S and the occurrences of these in the 100 experiments.
Yes.
We can start with the plotting these data points.
Yeah.
But then it's a limited, in a sense, a limited experiment, right? Because
right, sure. So I agree. I mean, 100 seems like a small value.
Yeah.
But let's forget about that. Let's say it was 10,000. Okay. And that sounds like, at least to me, that sounds like a large enough number that I could get a fairly serious distribution from that amount of data, right? So then what do I do?
You plot the PMF, right?
What is PMF?
Sorry, probability mass function.
Probability density function. Okay, yeah. Sure. Right. Okay. And what would that give you?
It gives you the ratio of S's in the first mutation. Of
ratio? You mean a distribution of?
Yeah. Sorry, a distribution of S. My bad. Yeah.
Distribution of S.
Yes.
And then what?
I thought we were plotting just that.
Yeah.
So do we also have to plot the distribution of time?
Not really. I mean, you could do that, and that they use that information for something else.
Okay.
But we are only concerned about the DFE here. So is that it?
You have to see if it matches your prediction.
Well, it doesn't matter, right? What the experiment tells you is if your theory told you something, maybe the theory is wrong.
Yeah.
Right? It doesn't matter. Whatever the experiment shows you is the truth. Right?
But I think it is the data is not relevant, not exactly relevant. It is not capturing only the beneficial mutations, right? It is the overall selectivity coefficient which is captures.
No, I no. What does that mean? Expand that.
We are presuming that all the change in the ratio is due to beneficial mutations.
Yes.
But we cannot be certain that the cause was a beneficial mutation, right?
What could have been the cause otherwise?
A deleterious mutation in the other population.
No, but the deleterious mutation is going to happen in one individual, right? That individual is going to get weeded out.
Oh, right, yeah.
Right. The entire other color can't have a deleterious mutation. Right? The numbers are very large here.
Then there can be a case where two different mutations are competing.
Yes, but that's why we are only interested in the first slope.
Yeah, but maybe at that time itself, there are already two different mutations which are competing in the population.
Agreed. But a very faint chance of that happening.
Okay.
Okay. Well, there are other reasons. Since these populations are large enough, there is a good chance that you could have different beneficial mutations also. But for reasons that I'll come to in a second, there is a very faint chance that that scenario plays out. It's not impossible, but the probability of that happening is actually very, very small. Something else we're missing here. So let's take a 2-3 minute break. I want you to think, why is the distribution that I got from this experiment not the DFE? Is the question clear? I get some distribution, but that distribution is not the DFE, right? Let's take a 2-minute break, and I will come back and I want your thoughts on it. All right, what do we think? Anybody? Why is this distribution not the DFE? Yeah, Yash, go ahead.
Maybe we are restricting it to the first mutation occurring, right?
Mm-hmm.
So it does not give us the whole picture.
What do you mean?
So I mean, because we are restricting to the first mutation itself, there might be other mutations occurring in the later stages with higher values of S, but we are missing them completely.
No, but that's not fair, right? Because the later mutations, they could occur in the original genotype or they could occur in the new genotype, right? If they occur in a new genotype, I'm not interested in that because I'm interested in the DFE of the original genotype, right? And if the later mutation occurs in the original genotype, sure, that could happen, and maybe I'm missing out on that information, but that is the reason why I'm repeating this experiment for 10,000 times.
Yeah.
Right? Anybody else?
So the distribution obtained from this might be very discrete, not very continuous, because few fitness values frequency we could have not obtained because of something like clonal interference or something like that.
Well, clonal interference, no, because again, I'm looking at only the scenario where the slope changes for the first time, right? And it will be discrete, and in the paper they do it for 100 times, but and obviously 100 is not enough. It's going to be very clunky sort of a distribution, but there was a larger issue associated with it, which is why even if you did 10,000 and you got a very smooth distribution, the problem will still persist. Okay. Anybody else? Let's take a look at the distribution that they did get. This is what they got. Sorry, too small. Or yeah, well, it's out of the distribution as well. Okay. So this frequency is about 17. So the whole thing is about 100, or there or thereabout. Okay. So this is definitely not exponential. Right. Here is the answer. Remember when we did the discussion of beneficial mutations occurring in a population? A beneficial mutation occurs and goes through two distinct phases. What were those phases? What needs to happen for a yes, go ahead.
There was a drift phase, and then there was a fixation phase.
Correct. So there was a Sakshi, go ahead.
I was saying the same thing, fixation or elimination.
Exactly. Right. So when a beneficial mutation first occurs, we saw that it underwent a phase where it was more beneficial mutation is obviously advantageous, but because its numbers were so slow in a chemostat type of a setting, there was a good chance that it would actually get washed away, right? And hence it would that beneficial mutation would be lost from the population. And it was only when the beneficial mutation reached establishment, right? Its frequency of individuals carrying that beneficial mutation reached a number of the order of 1 upon S. So if you're talking of a beneficial mutation of 1% advantage, then it's only when that genotype reaches a population of around 100 that we can say that drift is largely insignificant now, and it's selection which is going to dictate the trajectory of the frequency of these type of individuals, right? So does anybody want to answer now? Why is the distribution? Go ahead, Namrata.
So the distribution will become biased now because the ones with lesser selection coefficient can't be identified many times.
Yes. So what is exactly? So what is happening? So what is happening is that what we are interested in, we are interested in DFE. Hence, what we are interested in experimentally is the occurrence of these beneficial mutations, right? The probability which with a beneficial mutation of a certain S occurs in the population. However, in the experimental scheme that we are looking at, we are not looking at occurrence of those beneficial mutations. We are looking at only those beneficial mutations which survive drift, right? Which actually make it past the establishment phase. Hence, the distribution that we are looking at and the distribution that we started with are actually two different things. Does that make sense?
Yeah.
Right. Questions with that? All right. Now, if they had stopped here, that would have been one thing, right? But they realized that, and I think that's why they stopped with just 100 odd repeats of the experiment, right? So they say, fine, we've run into a problem, but so this is what I was like. When we do this, we get a DFE that we observe, but this is not the DFE, right? This is not the DFE because DFE is occurrence, whereas this is what I observe. This is distribution of mutations that made it past establishment, but that's not what I'm interested in. So here is the really clever thing that they did. Now, this is the approach. What they are saying is that there is an underlying DFE, okay? And just stop me if I don't make sense here. There is an underlying DFE. I have no idea what is that distribution, right? And this is the distribution that I want to find. Now, what happens is that mutations will occur in the chemostat according to this DFE, because that's a definition, and then drift plus selection will act on these on the beneficial mutations that are occurring in a rule consistent with this, in a statistics consistent with this DFE. Beneficial mutations occur and then they get acted upon by drift and selection. Remember, in that establishment phase, drift and selection are both relevant, and obviously after the establishment phase, it's only largely selection. So these mutations get acted upon by drift and selection, and after the action of drift and selection, we only see not all of them will survive, but some will survive. And what we are observing from experiments is the distribution of mutations that survived the action of drift and selection. This is the distribution that we get. I mean, what they see is something like this, right? So now they say that they don't give up at this point. They say we can still find DFE because this observed distribution is something that we know experimentally. Our experiments gave data for this. So this distribution we know, right? The action of drift and selection, we know the rules by which these forces are operating in the chemostat. So now our approach to find the DFE will be that we are interested in that unknown distribution upon which, when these rules act, we will get this particular output, right? So does that make sense? Yes, no, want me to repeat?
So I didn't understand.
I'm sorry, one at a time. Sakshi, what did you say?
So I didn't understand actually.
Okay, fine. Yash, what did you say?
I said, how are they integrating the two? I was not clear on that.
Sure, that's fine. Anirudh, what were you saying?
I was just asking if they kind of superimpose a particular exponential function, a negative exponential function on this graph or something like that.
Yeah, yeah, sure. So let me repeat this thing again. So there is an unknown distribution, right? This is the distribution that I'm interested in. And beneficial mutations are arising in a statistical fashion which is consistent with this DFE. Now to find this, they say we don't know this, but this underlying DFE produces beneficial mutations. Those beneficial mutations get acted upon by drift and selection, leading to some being rejected because of the action of drift and some making it to the establishment phase when I will actually observe them. The distribution of the beneficial mutations that I'm actually able to observe is known to me because that's the experimental outcome. My experimental outcome, we now realize, is not the DFE, but it's actually the beneficial mutations that made it to establishment, past the drift phase. So I know this distribution. I know the rules of action of drift and selection, right? This is similar to what we did when we were finding out the probability of survival of drift or something. So these rules on the Moran process is something that we discussed. So we know these rules. We know the observed DFE. Now what I will do, I want to calculate what was the background DFE, which when acted upon by drift and selection, according to the rules that I know, Moran process for instance, will give me an output of beneficial mutations, a distribution which is consistent with what I observed experimentally. Right? So I know the rules, I know this experimentally. I want to use these two pieces of information to back calculate that what would have been the DFE which gave me this particular manifestation. Does that at some level make sense? I'll go into the details in a bit, but does that make sense?
Yes, sir.
Actually, yeah. All right. So then that seems like a fair thing to do. What are the unknowns here? There are two unknowns here. One is the DFE, right? The DFE could have any shape, and that's Anirudh, your question. That how do we still define a shape? And what they did, what was asked the following question: that we take an exponential distribution for DFE and ask
Hello.
Um,
Yeah, so I didn't contact sir specifically, but I think there is a power outage in the institute. Few of my friends there was saying so. So I think he'll mail us later. So should we wait? I mean, there is not much time left for the meet, so we can wait for a few minutes. But I think sir will summarize and then mail again.
right, you can wait till 11 maybe.
Yeah.